Hello again, and welcome to our lecture on polynomial functions and zeros of polynomials. You'll remember last time we talked about functions, and we analyzed their graphs, and we looked at the domain of a function, etc. Well, in this lecture, I'd like to focus in on a class of functions called polynomial functions. Let me give you some examples of some simple polynomial functions, and you'll see that they're pretty easy to understand. For example, the polynomial 2x plus 3, or the polynomial g of x equals x squared, or how about the polynomial 4x to the fourth minus 3x squared plus 2x minus 7. These are all examples of polynomials. The first one, 2x plus 3, has the x to the first power, and so that's a degree 1 polynomial. The second one, that parabola x squared, is degree 2, and the third example was a fourth degree polynomial. Now, I think you understand what polynomials look like. Here's the formal definition, and like a lot of mathematical definitions, this looks pretty complicated, but let me go through it for you. So let n be a non-negative integer, and consider a sequence of numbers, a sub n minus 1, down to a sub 2, a sub 1, and a sub 0. These are the coefficients of the polynomial. And let's assume that a sub n is not 0. Then the function given by the following expression, and it's kind of big, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and you go down to a sub 2 x squared, a sub 1 x, plus the constant term a sub 0. That's a general polynomial. And we say it's a polynomial in the variable x, and we say it's of degree n because x to the n is the highest power in that polynomial. Okay. Let's focus on some polynomial functions. Let's start with, say, the linear functions. That would be a function of the form a sub 1x plus a sub 0. That's a first degree polynomial, but you usually don't see it written that way. Usually they'll write that as f of x equals mx plus b, or y equals mx plus b. And you'll recall that m is the slope of that straight line, and b is the y-intercept of that line. So these linear polynomials are straight lines, are graphs, are straight lines. Let's look at a particular example. How about y equals 3x minus 5? I claim this first degree polynomial is a straight line of slope 3 and y-intercept minus 5. You can plot some points in order to see what the graph looks like. For instance, when x is 0, y is minus 5, and in fact that's the y-intercept at 0 minus 5, isn't it? And then we could, let's say, x be 2, and if you plug 2 in, you get y to be 1. So both those points are on the graph, and then you join those 2 points with a straight line, and you see the graph of the linear function, the polynomial of degree 1, 3x minus 5. Okay. Let's remind ourselves of some facts about lines. What happens, for example, if you have 2 parallel lines? How are the slopes related if you're given 2 parallel lines? Yeah, right. If they're parallel, then they have the same slope. Here's a tougher question. What about if you have one line perpendicular to another line? How are the slopes then related? Okay, now they are negative reciprocals of each other. For instance, if the slope of one line is 3, the perpendicular line will have slope minus 1/3. How about a horizontal line? What's the equation of a horizontal line? Well, now the slope is 0. There's no rise. It's a slope 0, and that line has equation y equals a constant. That constant is where the line touches the y-axis. Well, here's a tougher question. How about a vertical line? Well, let's step back a moment. Is a vertical line even a function? Imagine a vertical line. Does it pass the vertical line test? No. So it's not even a function. But it still has an equation. It's just not a linear equation. And you can describe a vertical line by the equation x equals a constant. And that would be an equation for a vertical line. So let's move on to quadratic functions. These are parabolas. And the general formula would be something like ax squared plus bx plus c, and now a will not be equal to 0 to make sure it's degree 2. And as I said, these are parabolas, the graphs of quadratic functions. Let's look at a couple of simple examples to get a feel for the kinds of graphs that will appear. Let's look at x squared, f of x equals x squared, and a related parabola, a related quadratic function, g of x equals x squared minus 4. Okay, f is our standard parabola. It goes through the origin. It has one intercept, 1, 0 at the origin. What about x squared minus 4? Well, I claim it has 2 zeros now. It touches the x-axis twice, at 2 and at minus 2. And you can see that by factoring g of x. It factors into x minus 2 times x plus 2. By the way, let me make a comment about factoring. Factoring's tough. This one wasn't so bad. But in general, in mathematics, it's difficult to factor. I'll come back to that difficult issue later. Here are the graphs of those two parabolas. Notice how they're related to each other. There's x squared, the green graph, and then down below it you have x squared minus 4. It's the parabola shifted downwards 4 units. And notice that that graph of x squared minus 4 touches the x-axis at minus 2 and at 2. It has 2 zeros. Well, I've used the term zero. What's the technical definition of a zero? Well, a zero of a function is a number a such that f of a is equal to 0. For instance, in that previous example, the zeros of the function f of x equals x squared minus 4 are 2 and minus 2. A lot of people use the word root instead of 0. I use them interchangeably, and so I'll either call it a root or call it a 0. Basically, the zeros, or the roots, are where the graph of the function touches the x-axis. Okay? And as I said, it's hard to find. They're hard to find sometimes because it requires factoring, and factoring is a difficult process. Now, with quadratic polynomials, you can easily find the zeros, or the roots, using the famous quadratic formula. So let's review this quadratic formula. If you have the polynomial ax squared plus bx plus c, and you want to know what its zeros are, what its roots are, the quadratic formula tells you a straightforward formula. Here it is, and I think you probably remember this. The zeros are x equals minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now, a couple of points here. You see that symbol plus minus. Basically, that means that there are potentially 2 roots, one of them using the plus sign and the other one using the minus sign. When we do an example, I'll illustrate what that means. Something else kind of interesting, this is a universal formula. I've taught mathematics in various countries, and it's the same formula everywhere. It's always amazing to me. When I taught it in Bogota, in South America, it was the same formula, but in Spanish. Menos b, más o menos la raíz cuadrada de b cuadrado menos 4ac, todo dividido por 2a. It was the same formula. Okay, let's use it. Let's look at an example like 2x squared plus x minus 3. There's our quadratic polynomial, 2x squared plus x minus 3. I want to find the zeros. Where does this polynomial touch the x-axis? Okay, we use the quadratic formula. Here we go. It's minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Who are the characters here? Well, a is 2, b is 1, and c is minus 3. So we plug those in. X equals minus 1, that's minus b, plus or minus the square root. Here we go with that radical. B squared minus 4ac, 1 squared minus 4 times a, and a is 2, times c, which is minus 3, all divided by 2 times 2, 2 times a. Now let's simplify. Okay, minus 1 plus or minus, and what's happening inside that radical? Well, things are pretty nice. I rigged this problem to come out fairly nice. It's 4 times 2 times minus 3, that's minus 24, but it's minus that quantity, so it's really plus 24 plus 1. So inside the radical, it compactifies to 25. Nice. And then the denominator becomes 4, 2 times 2. So it's minus 1 plus or minus the square root of 25 over 4, which of course is minus 1 plus or minus 5 over 4. And now we'll see how to use that plus or minus symbol. When it's plus, you get minus 1 plus 5 in the numerator, and that's 4 divided by 4 is 1. So 1 is the first root, and the other one is minus 1 minus 5, which gives minus 6 over 4, which is the same as minus 3/2. So this parabola touches the x-axis twice at 1 and minus 3/2. I invite you to graph this parabola with your graphing utility and verify this algebraic result. Okay. That was pretty good, I thought. We can use the quadratic formula. I'm going to do another example with the quadratic formula, and things won't be so nice. Watch what happens now. An innocent-looking polynomial, x squared minus 2x plus 13 over 4. Let's apply the quadratic formula. So it's minus b, and b is minus 2, so it's minus a minus 2, plus or minus square root, and here's what's inside the radical, minus 2 squared, that's the b squared, minus 4ac, minus 4 times 1 times c, which is 13 over 4. And now some things cancel. The 4's cancel inside the radical, and we're left with 4 minus 13 inside the radical. So we have x equals 2 plus or minus the square root of 4 minus 13, all divided by 2. And 4 minus 13 is minus 9, and we have the square root of minus 9. Uh-oh! We aren't allowed to take square roots of negative numbers, are we? What do we do? Well, this polynomial doesn't have any zeros in the real numbers. It does not touch the x-axis. Okay. Now, that said, next lecture, we'll talk about complex numbers, and we'll confront this issue of square roots of negative numbers. But for now, there are no real solutions to this polynomial equation. How interesting. I want to look at this same example with a slightly different focus and use a different pre-calculus skill that's worth pointing out. So let's consider that same polynomial, x squared minus 2x plus 13 over 4. And now I'm going to do something called completing the square. This is a key calculus topic. When you take a calculus class, you often have to complete the square. Let me remind you how this goes. Take the x squared minus 2x and put them in parentheses, and we're going to add something to that expression so that it becomes a perfect square inside the parentheses. And then take the constant term, 13 over 4, and put it over there on the right. You're not going to need that for the moment. So what should I put in there to make it a perfect square? Well, I think you see if I add 1 to it, then it's x squared minus 2x plus 1, and indeed that's a perfect square. It's x minus 1 quantity squared. But if I put a 1 in there, I've changed the problem, so I have to subtract 1 outside. So now the constant is 13 over 4 minus 1. So finally, when I factor that perfect square, I have f of x equals x minus 1 quantity squared plus 9/4. Well, this is an interesting version of that original quadratic polynomial, because look what happens here. What's the smallest f of x can be? Well, if x is 1, then you get 0 squared plus 9/4, or 9/4. And for any other value of x, it's bigger, because you're adding a positive number to 9/4. In other words, this parabola has a vertex at 1, 9/4. Here's a picture of that parabola. Isn't that an interesting picture? It's got the vertex down there at the point 1/9/4, and it grows on both sides. And in particular, it never touches the x-axis, does it? It has no real zeros. And that's why the quadratic formula gave the square root of a negative number. Now, students often ask me, when I'm talking about the quadratic formula, they ask, hey, is there a cubic formula, Professor? Is there a fourth degree formula? In other words, if I give you a cubic polynomial, is there a similar formula to the quadratic formula? It might be bigger and uglier. And the amazing answer is yes, there are formulas for cubic polynomials and fourth degree polynomials. These formulas were developed by the mathematician Cardano in the 1500s. He developed formulas for solving cubics and for fourth degree polynomials. So then you might ask, what about fifth degree polynomials or higher degree polynomials? And the answer is, amazingly enough, no. There are no formulas for fifth degree polynomials and higher. Formulas that would look like the quadratic formula. This was proven back in 1824 by the Norwegian mathematician Niels Abel. It's not that mathematicians haven't found the formula for fifth degree polynomials. Abel did much more. He was able to show that there is no such formula, and there never will be. It's an amazing theorem of higher mathematics. Kind of amazing that you prove something will never exist. Okay, let's do some more examples. Let's talk about a fourth degree polynomial and talk about its root structure or its structure of zeros. How about the polynomial minus 2x to the fourth plus 2x squared? Let's find its zeros. Well, we factor it, and we get, let's factor out the term minus 2x squared, and then we're left with the quantity x squared minus 1. And then we can factor x squared minus 1 into x minus 1 times x plus 1. So in factored form, you can see the zeros right away. They are 0, 1, and minus 1. In fact, the number 0 is repeated. We often call this a repeated root because it occurs twice. Okay, suppose you wanted to graph this fourth degree polynomial. How could you attack it? What kind of skills could you bring into play? Graphing's difficult, but let me show you some of the behavior of polynomial functions that might be helpful in graphing it. One thing you might look for is what happens to this graph when x is really, really big, like 1,000,000. Well, notice that the minus 2x to the fourth term will dominate when x is large, and that goes off to minus infinity. So the graph's going to go downwards when x is large or when x is large negative. We also know the zeros of this function, 0, 1, and minus 1. Those are the intercepts. So this graph crosses at the origin and at the point 1, 0 and at the point minus 1, 0. And then you could plot some other points. For example, if x is 2, y turns out to be minus 24. And if x is minus 2, you also get minus 24. And you could plot some more points and then draw a smooth curve through these points. And your graph should look something like this. Notice the symmetry involved. This graph is kind of symmetric about the y-axis, isn't it? Something else interesting, you see the three zeros, minus 1, 0, and 1. But look at what happens at those zeros. At minus 1 and 1, the curve goes through the 0. It goes from underneath it to above, or from above down below. But at the origin, because it's a repeated root, it comes down and kisses the origin, then goes back up again. It doesn't go through. That's kind of an interesting fact about roots that are repeated twice. So we noticed the symmetry of this graph, didn't we? It's symmetric about the y-axis, and that's called an even function. Technically speaking, an even function satisfies the equation f of minus x equals f of x. And then you have odd functions, and we'll see a lot of odd functions in this course. Odd doesn't mean weird. Odd means that f of minus x equals minus f of x. And these are functions that are symmetric about the origin. A typical example is the function x cubed. That's symmetric about the origin. So graphing that polynomial was pretty difficult, I thought. We plotted some points. And by the way, your graphing calculator could produce the graph of that function. A graphing calculator is nothing more than a point plotter, a very fast-moving point plotter. So it does it a lot better than we can do by hand. But it's not very deep. It's just plotting a lot of points on those little pixels. But you'll get the same picture. If you go on and take a calculus class, you'll learn other advanced techniques for graphing functions that will aid in finding where the graph is rising and where the graph is falling, etc. Okay, why don't you be the teacher now for a moment? Pretend you're the teacher and you want to make up a test question. You'd like the question to be a polynomial that has a certain set of zeros. And then you're going to give this polynomial to the students who are supposed to find the zeros. And suppose you'd like to have a question say that the zeros are 2, 3, and 3. Let's find a polynomial with those zeros. Okay, well, I think it's pretty easy to see what to do. You would take the factor x minus 2 and then x minus 3 twice because it's a repeated zero. So it's a cubic polynomial, x minus 2, x minus 3, x minus 3. And then you could multiply that out. Now, I won't bore you with the details of that multiplication process, but at the end, if you multiply that all out, you get the following cubic polynomial. X cubed minus 8x squared plus 21x minus 18. There's a cubic polynomial. And this is the problem you'd give your students. This is why it's fun to be a teacher. You can give these hard problems to students. You would ask the students, would you please find the zeros of this cubic polynomial? And they would have to factor it, wouldn't they? And that's difficult to do. So it's much better to be the teacher than to be the student. Now, how can you find the zeros of polynomials if you don't know where they are, if you don't know even where to start? Where can you locate them? Well, let me show you a quick example of a technique for locating zeros. Suppose you have the polynomials 3x to the fourth plus 4x cubed minus 3. And by the way, this is a very difficult polynomial to factor. So where are the zeros located? Well, notice the following. F of 0, if you plug in 0, you get minus 3. And if you plug in 1, you get 3 plus 4 minus 3, or 4. In other words, the function is negative at 0, 0 minus 3. And then when you go up to 1, it's positive. So in that interval 0, 1, the graph goes from negative to positive. There must be a 0 in between. Isn't that neat? And in fact, using a calculator, you can actually find that 0, and it turns out to be approximately 0.779. In fact, it's even more interesting. If you graph this curve, and here's a picture of that fourth degree polynomial, it has two zeros, and one of them is 0.779, the one we talked about between 0 and 1, and that's an approximation of the 0. And there happens to be another one over there between minus 2 and minus 1, and that 0 is approximately minus 1.585. Well, the skill we just employed there, going from negative to positive, is an example of a very famous theorem, very important in calculus, called the intermediate value theorem. Let me state the theorem, and then I'll show you a picture that makes it all clear. So let a and b be real numbers such that a is less than b. And consider a polynomial function f such that f of a does not equal f of b on the interval ab. So it turns out then, on that interval ab, f of a and f of b are different, and the function takes on all values in between f of a and f of b. In particular, if f of a and f of b are of opposite sign, one's negative and one's positive, it takes all values in between, including the value 0. In fact, that's what we just did in the last example. This theorem is very important in calculus classes and is true not only for polynomials, but for many other so-called continuous functions. Here's the picture of what we're talking about. There's a and b down on the x-axis. A is less than b, and then we have our polynomial, and f of a and f of b are different. The theorem says that if you pick any number d in between f of a and f of b, then there'll be some c value in between a and b such that f of c equals d. It takes on all values in between f of a and f of b. Great. Okay. Let's turn to an application. Let's have some fun. Suppose you're a rancher and you're going to fence in 2 rectangular enclosures for your horses and your cows. And you have 200 feet of fencing. And you're going to make 2 corrals, and you want to make these as big as possible. You want to have room, a lot of room for your horses and your cows. So basically, you want to keep the horses and cows separate from each other. So our picture is going to be with a fence down the middle, and on one side are the horses, and on the other side are the cows. So here's the setup. You could label your 2 corrals with y being the length vertically here, and then x being the other dimension of one of the corrals. So according to this picture, what's the total area of our 2 corrals? Well, the length is 2x, and the height is y. So the area is 2xy. That's the area of our corral. And we have 200 feet of fence. That means that 4x plus 3y equals 200. 4x meaning xx on top, xx on the bottom. That's 4 x's, and there are 3 y's because there are 3 fences going vertically in the picture. So now we have the area equals 2x times the quantity, 200 minus 4x over 3. Now I'm going to do some algebra now. It's kind of ugly algebra, but I'm going to complete the square of this polynomial in x. First, I'm going to pull the 3 outside and move the x inside the parentheses, so I get 2/3 times 200x minus 4x squared. Now I'm going to move a 4 outside, so I get 8/3 times the quantity 50 minus x squared. In order to complete the square, I want to have the x squared term positive, so I'm going to move a minus sign out. And I have now minus 8/3, and now it's x squared minus 50x. Those two flip-flop. And let's complete the square. What's the rule? The rule is you take the b term, the middle term, minus 50, divided by 2, and square it. So I'll have to add 625. So now I have minus 8/3 times x squared minus 50x plus 625. Well, now wait. I've changed the problem. I've added 625. Well, I didn't really add 625. I added 625 times minus 8/3, didn't I? So I have to put that back. So at the end, I put in 625 times 8/3, so I don't change the problem. And now that thing in parentheses, x squared minus 50x plus 625, is a perfect square. It's x minus 25 squared. And I have my formula for the area, minus 8/3, x minus 25, all squared, plus 5,000 over 3. So I want to maximize this. Well, notice that the minus 8/3 x minus 25 squared is at best 0, otherwise it's negative. So let x be 25, and that will maximize a. And with picking x 25, you can calculate the y value. It'll be 200 minus 4 times x, or 4 times 25, all divided by 3. So y turns out to be 100 over 3. Here's a graph of that area function that we just talked about. And notice the high point of the parabola occurs when x is 25. Isn't that interesting? We were able to find the maximum value by writing the parabola using the completing the square skill, and then we discovered the high point. All right, good going. I think we had a lot of fun looking at polynomial functions, their roots. We made a an issue that it's difficult to factor. I'm the first to admit that. Fortunately, there are computer programs and calculators now can factor polynomials pretty well. What are we going to do next? Well, remember that some polynomials didn't factor. For instance, x squared plus 4 cannot be factored using real numbers. It doesn't have any zeros in the real numbers. Well, next time we'll introduce the so-called complex numbers. I think you'll find this a really interesting lecture next time. Complex numbers are, I shouldn't say the word strange, but they're fascinating. And in fact, not only will we study complex numbers next time, but we'll look at some applications of complex numbers to what are called fractals. And in fact, we'll see the very famous Mandelbrot set. So I look forward to our next lecture on complex numbers, and I hope to see you soon. Thank you.